This is predominantly a thermodynamics question from year 13 with some amount of substance. There's an ideal gas equation calculation coming up later. So 11 marks in total, 4 sections, have a go at each bit and then review. So here's part A, part B, part C, and finally part D. So if we take a look at part A, where we're completing the Bourne Harbour cycle, you have got to remember that in a Bourne Harbour cycle there is only one change made on each step. So at the moment I can see that I've got solid sodium and half F2 gas, and over the course of the steps that are taking me up to the top line I have got to atomise and then ionise the sodium. So it makes sense to atomise each of the two components. Now, enthalpy of atomization is the enthalpy change when 1 mole of gaseous atoms is formed from its elements in their standard states at standard temperature and pressure. So in my first step, I'm going from Na solid to Na gaseous. But I'm being very, very careful that I keep the half F2 exactly as it was. Because in my second step, I'm going to keep my Na gaseous as it was, but I am atomising my fluorine and making 1 mole of gaseous F. Onto the calculation, and I've transferred the cycle over so that I can substitute the figures in from the table. And if you take a look, I've taken them exactly as they are, apart from one, because we've actually been given the bond dissociation enthalpy for F2, which is twice the enthalpy of atomization of fluorine. That's why I've got plus 158 divided by 2. My next step is to identify what the two routes are, and I've done those as a blue route and a green route, and I'm going to highlight those colours with the blue and the green so we can see where they come from. Rearranging this to make X the subject takes us to an enthalpy value of negative 903. Moving on to part C, and we want to know how the enthalpy, the lattice formation enthalpy I should say, of NaCl compares with that of NaF, and reasons must be given. Now it makes sense to start with the reasons sometimes and think about what is the difference between NaCl and NaCf. And the first thing that I hope stands out is that a Cl- ion is bigger than an F- ion. That's the only significant change. The Na pluses are identical, their charges are the same, it's the size on these ions that's important. Now because the Cl- ion is bigger, there's a weaker attraction to the Na plus ion within NaCl. The impact of that is that the formation enthalpy is less exothermic for NaCl. Moving on to part D, and this is the ideal gas equation. I'm going to recommend, as I do on every one of these videos with ideal gas, start off by writing down the 5 different components and then fill in what you can from the table. We know we want volume, so that's X. We've got P, R and T provided, but we haven't got N. What we do have is a mass of sodium fluoride. So I can work out 2.38 by 10 to the minus 2 moles of sodium fluoride. However, that's NaF, and fluorine exists as F2. So if we want the moles of fluorine gas, we're going to divide that by 2. We get 1.19 by 10 to the minus 2. I've also, you'll notice, converted my pressure into pascals. Then I take my PV is nRT equation, rearrange it to make V the subject, and then substitute the figures in. And as I do that, I get to a value of 2.95 by 10 to the minus 4. But here's the problem, the volume is in meters cubed. To convert it to centimeters cubed, I'm going to need to multiply that by 10 to the 6 or a million. That takes me to the final answer of 295 cm cubed.